Hello, Mr. Simpson here with our section 14.7 acid-base titrations video. As always, please go ahead and pause the video and copy down your learning objectives. So let's start this unit by talking a little bit about what a titration is. Okay, so this is a technique that we use to determine the concentration or pH of an unknown solution. So we'll work through a couple different types of problems in which we do those two things. You can see the setup here on the left, a little closer view of a titration setup. We're going to use a burette and a flask. In the burette, we'll put our titrant. So this is what we know. This is our known solution. So if we have a known solution concentration of base, that'll go in the burette. The analyte is the solution of unknown concentration, and that's going to be located in the flask. Okay. On the right, you can see the titration of an oxalic acid, and so what's happening here is in the flask we have our acid, and we are slowly adding in our base until the endpoint is reached. And we'll use an indicator solution. In this case, the pale pink indicates it's likely phenolphthalein, and that color change of that solution will occur when we've reached the endpoint. And I'll talk a little bit about endpoint and equivalence point here in a second. But the goal here is to get this faint color change throughout the solution. You can see in these first couple steps as we titrate in our base, we will start to see that color showing up, but it doesn't maintain for a period of time in the entire solution until we've reached that endpoint. As I said, the two terms, equivalence point and endpoint, are similar yet a little different, and you can see those distinctions in this table. I want you to go ahead and pause the video for a moment and read through the information provided here. So really the biggest distinction is the equivalence point is kind of where it ends, and the endpoint is indicated by a color change. So if we had a pH meter in our analyte as the titration was happening, and we were collecting this data of the pH as we were adding base, we would be able to then identify the equivalence point, where that reaction ended, and that is you can see here for a strong acid, strong base. We are going to be actually doing a titration not with a pH meter but with an indicator solution. So when I use an indicator solution, then what I'm finding is the endpoint. Okay, so as it says here, it does not always give the point where the reaction ends. It comes either almost with the equivalence point or after the equivalence point is where the endpoint's going to happen. Okay. The other thing I would like to point out here in these two graphs is the difference between, and we're going to focus this year solely on strong acid, strong base titrations. But just for a point of reference, in the first graph, I have a strong acid, strong base, so the equivalence point is exactly at a pH of 7. If I had a weak acid being titrated by a strong base, our equivalence point is going to be a bit above 7. Okay, and the reason being because of the effect the strong base has on the strong acid. They're not equal parts as they would be in a strong acid, strong base. So the base kind of overpowers the weak acid a bit, and we get an equivalence point higher than 7. Okay, let's get into our first type of problem here, determination of to determine concentration. So I talked about determining concentration or pH of an unknown solution. So in our first example, we're going to determine concentration. Go ahead and pause the video and copy this problem in your notes. All right, this problem is pretty straightforward because we have a strong acid and a strong base that is more specifically in a 1-to-1 ratio. So when I have a strong acid reacting with a strong base, what I produce is water and a salt. And so because our relationships here, because our ratios here are 1-to-1, we're going to see that a pretty straightforward calculation here utilizing this formula. Okay, so this really is just a plug and chug situation. So I have the molarity of my acid times the volume of my acid equals molarity of my base times the volume of my base. Again, what is the problem asking for? What is the problem giving me? It's asking for the concentration of the acid. So I am looking for this value here. I know, remember, molarity is moles per liter. Okay, moles per liter. So these volumes that are in milliliters need to be converted. So I would have my molarity times my volume of my acid, which would be this value in liters times the concentration of my base times the volume of my base, again in liters. And a pretty straightforward calculation here would allow me to calculate the molarity or the concentration of my acid to be 0.690 molar. Okay, I have a second question here that is a little different. There's an added wrinkle here, and that is the fact that if you take a look at our acid in this problem, it is what is known as a diprotic acid. So unlike HCl that had just one hydrogen, H2SO4 has two hydrogens. So let me just skip ahead here for a second and talk a little bit about monoprotic versus polyprotic acids. So the HCl we saw in our first example was in our first problem was an example of a monoprotic acid because it only has one ionizable hydrogen. If I have more than one, it would be considered polyprotic, where something like the carbonic acid you see here has two hydrogens. So technically, a classification of polyprotic here, this would be diprotic. And if I had something with three hydrogens, like phosphoric acid, this would be triprotic. Thinking back to our Ka values, this actually means that I can lose multiple or ionize multiple hydrogens, and that means I can get, for one acid, I can get multiple Ka values. This time sometimes just referred to as Ka1 and then Ka2. Okay, so there is a Ka for each of the hydrogens that is ionizable. Take a notice here, you will see that obviously with each successive ionizable hydrogen, the Ka value gets smaller, so it becomes a weaker acid. Okay, let's get back to our calculation here, our problem. So I have to handle this problem a little differently because it is not a one-to-one ratio. If I think about what my reaction looks like here between my strong acid and strong base, I would produce water again, but this time I'm going to produce a salt that looks like this. And you can see here I have some balancing to do. So if I put a 2 here, I should have, this should now be balanced. Sorry, and a 2 here. This should now be balanced. Okay, so you can see here for this titration that's occurring, I am not in a one-to-one ratio as I was before, but my stoichiometric relationship here is a 1-to-2 ratio. So that means I have to do a little bit more in my calculation, or I just need to account for that in my calculation. Okay, so the endpoint or equivalence point is where the moles of acid equal moles of base. Okay, moles of acid equal moles of base. When we do our titration with an indicator solution, we want to get the faintest of color change happening because that color change will occur when my solution has gone from acidic to basic. So the slightest color change means that I'm getting that rapid change in pH occurring. Okay, and my moles of my acid equal my moles of base. So based on the data that this problem has provided, I can use the molarity of the base times the volume of the base to calculate moles of base. Okay, and then from there, I can convert to knowing our stoichiometric relationship, right? That I know that it's not, I wouldn't have the same, I wouldn't have 0.00808 moles of acid. I would have, as I look at the balanced equation there, my relationship here is a 1 to 2 relationship. So I would actually have 0.00404 moles of acid at that endpoint that we saw with the color change. Okay, so now that I know moles of acid and I know how much acid I had in, the problem told me I had 26.60 mils of acid, I can now calculate my concentration. So I have my moles divided by the volume, and I get a concentration here of 0.152 molar. Okay, so just be careful of that as I'm looking at the acids and bases being used. If I have something other than a 1-to-1 ratio, I just have to do a little extra. I cannot just straight away use this relationship, molarity of acid, volume of acid, molarity of base, volume of base. Okay, let's now transition to the next type of problem in this unit, which is to determine the pH at points throughout the titration. Okay, so points throughout the titration, okay, so think about what that means is we have, before the start, so I have the pH of my analyte before I've started to titrate in any base. I've started my titration, but I have not reached that equivalence point yet. I haven't seen the color change in my using my indicator. At the equivalence point, I've added enough base to get that color change, and I see the end point. So I'm at that point, and then of course after. So at any point along the way, it could be important for us to know and understand what the pH of our solution is in our flask. Now, each step of the way, I'm going to handle this slightly differently. Okay, the first step is pretty straightforward. As I take a look here, prior to the addition of any base, I have a strong acid, so the concentration of my acid equals the concentration of my H3O plus. I've symbolized strong acid here with SA. So my H3O plus and concentration of my strong acid concentration are the same, so I just simply take the negative log of that value given to me in the problem. Okay, I have to do a little bit more here before the equivalence point. Okay, so remember that we're working in moles, so I would be given data that would allow me to determine moles of both the H3O plus and the OH minus. Okay, they'll give me molarity and volume. I can determine the moles of both. Okay, now I want to subtract the difference, and since it's before the equivalence point, I'm going to have more moles of H3O plus. So my moles of H3O plus originally will be greater than the moles of OH I've added at that point, which means that my difference will be the moles of H3O plus I have. Once I have moles of H3O plus, you can see here, I can then divide it by the total volume of solution of the acid and the base combined to get my concentration of H3O plus, and then I can calculate my pH. So I have a little example problem here that I kind of walk through those steps to show you again. What is the pH? And you see here, as I mentioned, we've got the data for both our base and our acid. Okay, so step one is to determine the moles of both. So you can see this should actually be, these are both step one. I'm determining the moles of both. So The volume in liters times the molarity gives me moles of both. All right. Then I am going to subtract and determine the difference. And you can see I had more moles of H3O plus, so my difference is moles of H3O plus. We can also see then that once I have that, I can divide it by my total volume. Again, because we had 48 milliliters and 50 milliliters is 98 milliliters. That's where the I'm a little off here. That's where my volume comes here. And then once I have that concentration, I can solve for the pH. I'm going to walk through some more problems at the end of all this as well. The next possibility we said was at the equivalence point. This is a simple one. If I know I'm at the equivalence point, then the pH is 7. Okay, at the equivalence point for a strong versus strong, we saw it on the graph, our pH is 7. And now after the equivalence point, it's going to be very similar to the process before the equivalence point. The difference being that now I'm in a situation where my moles of OH added is more than the moles of the H3O plus originally. And so I'm going to have to, when I do this subtraction here, I'm in a situation where we're going to end up with more moles of OH minus, get the concentration of that OH minus, and then going to remember when I take the negative log of that value, I'm going to be calculating the POH, not the pH. So I have to finish off with that subtraction. You can see here I've listed kind of those overall steps generically one more time. You may want to make sure you have those copied down in your notes, and then go ahead and copy this practice problem, and we will work through this together. Let's start with part A. This is obviously before any base has been added. So as I said in the notes before, for part A here, this is going to be pretty straightforward. It's going to be the concentration of the H3O plus is going to equal the concentration of the strong acid. So they gave me the concentration of the, they gave me the concentration of the strong acid as 0.100 molar. So that means to calculate the pH, I'm just taking negative log of 0.100 molar, and I'm getting a pH of 1.00. So whatever the concentration they give me in the problem, that's the concentration of my H3O plus, and take the negative log of that value, and I have my pH. Okay, next let's look at B. And for B here, I'm going to follow the process. So I'm going to first find moles of both. So I'm going to have there's my moles of HCl. I'm going to do the same thing with the data to determine my moles of my NaOH. So in part B, we are adding 12.5 milliliters, so that would be 0.0125 liters. Okay, step 3 is to subtract the mole values. So larger minus the smaller here, so it's going to be 0.00250 moles of HCl, or we'll kind of actually just consider that the acidic piece, the H plus or the H3O plus, minus our 0.00125 moles of our basic OH minus. And you see that I'm going to have a greater amount of, so I'm left with 0.00125 moles of my H plus. Okay. The next step is to find the molarity of what's remaining. So I'm going to take that mole value after the subtraction, and I am going to divide it by the total volume. So at this point, my total volume is 25 plus 12.5, because we have titrated in 12.5 milliliters of base. So in terms of liters, that is this. and I'm going to get a concentration at this point of, for my H3O plus of this, and I'll just put, again, concentration H3O plus is what I'm solving for here, my molarity. All right, so that means now that I have my concentration of my H3O plus, I only have one thing left to do, negative log of H3O plus, and I would get a pH value here of 1.48. Okay. In part C here, we see that in both cases, in both my acid and my base, I have 0.1 molar solutions. So because I have the exact same molarity, and when I have the same volume, I'm going to have my concentration of my H3O plus is going to equal my concentration of my OH minus. So that means we're at the equivalence point. So here, no calculation needed. I have a pH of 7. Okay, now let's talk about D for a second. In D, I'm going to follow the same process as B. So I'm going to, we already know that we have, I don't need to recalculate my moles of acid. That has not changed because the volume of the acid has not changed. So I already know I have 0.00250 moles of acid. Okay, I've now added 37.5 or 0.0375 liters of base to my 0.1 molar base. So I can get here, I know I have 0.375 to 7 moles of base. Okay, now I'm going to subtract, and of course, this time when I subtract, I'm going to have a greater amount of my OH, or my basic component, than I am going to have of my acidic component. So I end up with, here with a similar value, but now that is moles of OH. Okay, so when I take that moles of OH and divide it by my total volume here, 37.5 plus 25, or 62.5 milliliters, or 0.0625 liters, I'm getting an OH minus concentration, because again, I had more moles of OH than I did moles of H, of 0.0200 molar. Okay, when I take the negative log of that, I'm not calculating the pH, I'm calculating the pOH. So I get a pOH value here of, 1.70. So then 14 minus 1.70 means I have a pH of 12.3. Okay, so after the equivalence point, I have more OH than H plus. So when I get that that concentration in the same way, I'm going to be actually having the concentration of OH minus. So when I take the negative log of that in comparison to here, I took the negative log because I had more H plus. I was done with I had the pH. Here, when I take the negative log, I will have calculated the pOH. So I have to do this 14 minus 1.7. You can see here, in both circumstances, I really just followed these 4 steps, as written to get to the point of being able to solve for my pH. Okay, that's all for this section. Good luck.